All right. Hi, everyone. I'm really excited to be here today at ScalaCon and to talk to y'all about data science in Scala with ScalaPy. So let's dive right into it. So first, why ScalaPy? So if you've seen a talk about ScalaPy in the past, this will mostly be familiar. But I think ScalaPy kind of has this kind of story around it about kind of what we're trying to bring to the Scala community and the Scala ecosystem. So I think it's important to revisit this. So currently, data science has a split ecosystem. We have Scala, which is built around this really high-performance infrastructure and distributed systems, whereas Python, which has a really great ecosystem around experimentation and trying new models and developing machine learning pipelines. And we see this reflected in the types of libraries that we have. So in Scala, we have Spark, which again is great for this super high performance handling large data sets. But on Python, we have libraries like NumPy, which are not optimized as much for distributed systems, but more on having a great experience when working with linear algebra on a local computer. So the question is, we have these two ecosystems, and they're both focused on the same goal, which at the end is to use data science to bring great experiences to users around the world, but they're split. So how can we bring Python and Scala together? And that's where ScalaPy comes in. So ScalaPy gives you 4 key things. It lets you use Python libraries from Scala code as if they were regular Scala APIs. You can do this in both JVM and native code. So ScalaPy supports both regular Scala running on the JVM as well as ahead-of-time compilation through Scala native to native code. It has a seamless interoperability layer. And we'll see this a lot later today, that using Python libraries really feels like you're just using a regular Scala library. And you can get a fully type-safe interface. And this is something we're going to be talking about later today as well, where you can interact with traditionally dynamically typed Python libraries from Scala with static types. So today I'm excited to announce ScalaPy v0.5, which just released today. The key focus of ScalaPy 0.5 has been on performance. So the main bottleneck when you're mixing Scala and Python code together is data transfers between the two. So with ScalaPy 0.5, sending data from Scala to Python is up to 5 times faster on the JVM. Reading data from Python into Scala is up to 4 times faster. You get a new ergonomic API for nested sequence transfers, and we'll see a little bit of this in action later. And I'm really excited about a pre-alpha static type facade generator. So now, without having to write any code by hand, you can get a statically typed interface to many of your favorite Python libraries. And we're going to see this later today. So before we get into kind of the key applications where we're going to explore how ScalaPy lets you implement data science applications, let's do a quick overview of what ScalaPy gives you. So first, talking to Python. So ScalaPy works by embedding a Python interpreter inside your Scala application. So whether you're on the JVM or in Scala native, ScalaPy uses a foreign function interface, either JNA or a CFFI that Scala native directly provides us to talk to a CPython interpreter under the hood. Now, what this means is that we're using regular Python that's off the shelf from the official Python implementation within ScalaPy, which means that you don't have to worry about any incompatibilities. Every library that works in Python normally will work in ScalaPy. And this gives you a huge ecosystem of libraries to work with. And ScalaPy offers you an identical interface regardless of whether you're on the JVM or Scala native. The only thing that changes is this layer under the hood. Now, when you're talking to these values in your Python land from Scala, you have to have a layer in between. So let's say in your CPython interpreter, you have a couple different values. You might have a list of a couple numbers, 1, 2, 3, or a module. In this case, we could have loaded TensorFlow. ScalaPy wraps over these with an intermediary layer called a Pi value. Now, this is a low-level value. You won't interact with this directly if you're writing Python ScalaPy code. But what this does is it gives us a nice referentially safe way to access Python values. So if you're referring to Python values, you can ensure that they won't be cleaned up if you're still using them in Scala. And as we'll see later, you can actually do the same thing in reverse, where Python code can safely hold on to Scala data. But then when you are actually accessing these values, so if I want to interact with a Python list from Scala, or if I want to talk to TensorFlow from Scala, you have these nice high-level APIs, and in many cases, statically typed APIs, which wrap around these Pi values and give you a nice Scala-like interface into these Python APIs. So that's kind of the core of how ScalaPy works. And you can see the paper that we published at the Scala Symposium last year for more details on the details under the hood. The next step is mixing Scala and Python seamlessly. We really want to feel like using a Python API is no different than using a regular Scala API. So the first step of this is dynamically typed APIs. By default, whenever you import, you're importing some Python library into Scala or using some built-in Python APIs, your interface will be dynamically typed. And that's because by default, Python is a dynamically typed language, and so we don't have static types that we can directly use. ScalaPy makes this really easy to interact with these dynamically typed APIs through Scala's dynamic feature. If you've used Scala.js before, you'll find this familiar because Scala.js lets you interact with JavaScript APIs through a similar dynamic interface. So for example, if I want to construct a list of numbers, I can just grab the global scope, pi.dynamic.global, and call the list API. And this really feels like it's just a regular Scala API, but under the hood, it's actually going into Python and calling the list function, which is available as a global function in Python. Then I can just call, for example, append, which under the hood will expand to this dynamic invocation. But to you as a Scala developer, it just feels like I'm calling a method append with a number 4. And even this number 4 will automatically be converted into the corresponding Python integer value. And then, for example, if I want to print the result of summing up a bunch of values in my list, I can do that. I get a Python value back as a result of that summation, but then I can print it using println, our regular Scala method. And so this way we can go back and forth between Scala APIs and Python APIs without really having to worry about where each API is coming from. Another feature that ScalaPy comes with is Python interpolation. So many times if you're working on ScalaPy code, you might find a snippet of Python on the web that you want to just kind of copy into your code just to get something running quickly. ScalaPy makes this easy by providing a string interpolator that lets you execute Python expressions. So for example, if I had a snippet of Python code where I'm summing up a list, I can use the pyquote interpolator to say call sum, and please put my list value inside as a parameter. And ScalaPy will automatically set up the scoping for this expression so that the $mylist will actually be replaced with a reference to the mylist value that we constructed earlier. So under the hood, again, this translates into the use of a Scala string context, which allows us to have these custom interpolators. But to you as a user, you can just have regular Python snippets that even mix in Scala values and just execute them without any trouble. Beyond this, we also have some Python syntax elements. So Python comes with some special syntax features that don't have a direct parallel in Scala. One of them is the with keyword. So what with lets you do in Python is kind of a try with resources. You can take a resource, temporarily open it, do some logic with that opened value, and then once you're done with that block, the resource will be automatically freed and closed. So if we wanted to use this keyword in Scala, ScalaPy has an API for that. All you have to do is pi.with, pass in the resource that you want to open. In this case, we have a file that we want to read, and then a callback which says, once you have this file opened, what do you want to do with it? In this case, we can just print out the encoding of the file. So basically, the goal of ScalaPy is anything that you can express in Python, you should be able to express in Scala. And that means that if there are any special syntax features, you can do that in Python as well. And this gives you a really seamless way to mix and match different APIs from Python into your Scala code. Now, something I hinted to earlier is there may be situations in which Python needs to call back into Scala. And ScalaPy supports that out of the directly as well. So for example, if we have a function myfunc, which just takes an integer and adds 1 to it, we might want to call, for example, the Python map function. So Python has a map function similar to Scala's, and instead of being called on a sequence, instead it's a global function where you pass in a lambda as well as the sequence you want to transform. So for example, I could call this Python function map, but pass in a Scala function. And ScalaPy will automatically set up the necessary hooks so that Python can safely reference the Scala code and call it. So now you get the seamless interoperability where I'm able to take Scala functions, pass them into Python code, call a Python function, and that will call back into my Scala code. So you can go back and forth without any trouble. And ScalaPy handles this all automatically under the hood for you, including all the conversions. For example, here, myfunc is going to be called with a Python integer, but ScalaPy will automatically convert the values back into Scala integers so that you can process them. Another kind of common situation that you have is sending sequences. So you might have some large collection of data, especially if we're working with data science, we'll have lots of data that we want to send from Scala into Python. And you can do this easily through the toPython proxy and toPython copy APIs. So let's dive into this a little bit deeper, because this is where things get a bit more interesting. So ScalaPy offers two different methods to take a sequence of data and pass it into Python. The first is a proxy, and this is kind of the most intuitive way. What a proxy does is it creates a shallow sequence on the Python side. And every time Python requests an element from that shallow sequence, it'll actually go back into Scala and get that element. So here, for example, if we convert our sequence, which prints every time a value is accessed, and send it into Python, the data is not requested until we ask Python to actually print out the values. And then we get these requests. But this isn't always great for performance, especially on the JVM, where the cost of crossing between Scala and Python can be a bit higher, since we have these native function calls involved. If you know that Python is going to be frequently accessing the same data, then you can just make a copy instead. So this has a higher cost initially, where you have to transfer all the data at once. But after you're done with that, Python can access this data super quickly, since it's all native to Python. So we can do that with toPython copy, and then we see here that all of the data is requested ahead of time. And a lot of the optimizations that I shared earlier about ScalaPy 0.5 come in these two APIs, where we're able to eliminate a lot of the overhead of them. So you're able to transmit data much, much faster. And this is really critical for data science applications where you might have a high kind of latency requirements, and you need to make sure that you can transfer the fresh data over to Python quickly to be processed. And ScalaPy 0.5 makes it a lot faster to do that. All right, so that is a really fast overview of what's available in ScalaPy. So first, let's jump into our first application, deep learning. And deep learning is one of the things that Python is most commonly used for. And it's something that as Scala developers, we're all very excited about, because it's a new domain where there are a lot of interesting possibilities. So before we jump into the coding, I just wanted to do a kind of a quick review of some machine learning concepts that we're going to be using today. So I hinted to this in my tweet earlier, where I had a picture of Elmo and Bert. Bert is a deep learning model developed by Google, which really demonstrated the power of this deep learning concept called a transformer. So real quick, I won't go into the detailed math behind this. You can check out the UC Berkeley CS 182 course, which is publicly viewable. All the lectures are there, and it's an excellent course. But there are two key elements here. So the first is an attention layer. What we're going to be doing in this demo is analyzing a bunch of text and processing it using a deep neural network. When you're processing text, you have unlimited length sequences. So you can't use a traditional neural network layer like a linear layer, which just takes all the inputs and processes it using a matrix multiplication. Instead, we want to exploit the structure of this data, where we have a bunch of words with some connections between them. And that's what attention layers are about. So briefly, what an attention layer does is, for each word in your sequence, the neural network is going to produce a key, a query, and a value. And this is kind of actually, I found this idea really interesting because it makes intuitive sense to me as just a regular software developer that maybe this is a way we can express these types of natural language problems in machine learning. So what do you do with these key queries and values? What you're trying to do is each word is querying the words around it to learn something about its context. So for example, if I have a sentence, the dog is cute, if I'm the word cute, I want to know what I'm describing. So I might want to know what the subject is, which is the dog. So my query is going to be a bunch of numbers, a vector, which represents that information that I'm looking for. I'm looking for the subject of the sentence. And when I'm processing the words the dog, my key, which is saying this is the information I have to offer, is going to be a vector similar to that query, saying this is the subject. Now what you do is once you produce all of these keys and queries, you use the dot product and a softmax layer, which kind of takes the largest value. So the largest value is going to be where those keys and queries line up. So again, we have cute is looking for the subject. So it's going to have a query looking for the subject. Dog is going to have a key saying I am the subject. The dot product of that will be high. And so when we perform the softmax, we're going to get a value close to 1, representing how important is dog for cute. And finally, once we know that, okay, cute was looking for the subject, we found the subject where we have a high probability that dog is the subject, we pull that data in, and that can be processed by a further layer. So basically, through these attention layers, you can have words request context about other words, get that context, and then continue processing. Now, when you stack these together with some additional nonlinearities in your network, you get what's called a transformer, and that's the picture on the right. So what's on the left here is a attention layer, and on the right is a transformer, which basically combines attention layers with a couple different elements that you need for natural language processing. I'll just point out one key element here, which is the position-wise encoding. So if you think about this, because each word produces a key and query independently of the others, we actually lose the order of words in our sentence, right? If we swap everything around, the keys and queries would still be the same because we're producing those independently. So what transformers do is we'll actually bring in some position information as well, saying this is the first word in the sentence, this is the second word. And then you can use that to kind of further guide your processing of text to make sure that you get the correct, you understand the order of what's going on in your sentence. Now, when you stack a bunch of transformers together, then you get GPT-2. I mean, this is a kind of rough description of what GPT-2 is. There's a lot more that goes inside. And the goal of GPT-2 is to complete sentences. So for example, if you use Gmail, you have similar technologies under the hood. When you type a couple words of a sentence, complete it, and you get the rest of your sentence. The way GPT-2 works is it's just trying to guess the next word in the sentence for each word of the input. And so if we want to generate a bunch of words, what we do is we start with our prefix. We say, okay, analyze what you have so far. What's the next word? We get that next word and just add it to the end of the sentence. And then we run the whole thing again, saying, okay, we have all these words plus the next word. What's the word after that? And we keep on repeating until we get a completion. So this is going to be a bit crazy and stressful. This is going to be probably one of the craziest live codings I've done. But today we're going to be using GPT-2 to complete Scala code using deep learning. And we're going to do this all with ScalaPy. So let me jump into VS Code. So we have 28 minutes left, so this should give us a good amount of time. So I've already set up a template. So we have a training app. I'm using Scala Meta. So what we have is a corpus of Scala code that I've pulled. Right now, we're just using one example Scala project, which is the Lila chess engine and website. So we're going to be learning how developers write Scala code based on Lila chess and trying to autocomplete Scala code based on what we learn. So you have some utilities. We're just going to get all the Scala files in our corpus. The first step we're going to do is parse our sources and get in statements that we're interested in. And we're going to be using Scala Meta for this. So Scala Meta is a great library that lets you parse and analyze Scala code. So what I'm going to do is I'm going to take the tree of data that we have. So this is a tree for a single Scala file. And we're going to collect some statements from this that we're interested in. So what we'll do is first, we'll just collect definitions. So we're interested in every time someone declares a value or a variable or a method. And those are kind of entry points to where we want to train our machine learning model for code completion. So if we get a node, which is a defin.val, we're going to produce one example from this node. Let me pull out my keyboard properly, which is a seek of just the node toString. So we're just going to get the body of that node. We'll do a similar thing. Let me just copy this. So we're going to do the same thing for variables and methods. Def and let's do var, def, and we'll also do classes. So now every time we see a val, var, def, or class in our training code, we're going to get a training example saying, here's text that a Scala programmer could produce. Another situation that we're interested in is regular statements. Like if I have a method, I want to analyze all of the individual lines one by one, saying this is a sentence we might want to autocomplete. So if we have a node, which is a term.block, so this represents a block of Scala code, what I'm going to do is take every statement. So we have a stats method, which gives us all the statements in our block, and get each of those statements converted to a string. And let me flatten this because we've been producing a bunch of sequences. All right, so what we're going to do is for every val, var, def, or class in our code, as well as every statement within a block of Scala code, we're going to get training data from that. And we're going to just get strings. All right, so far there's been no ScalaPy involved. We're just getting all the Scala files. Now we have some ScalaPy involved. So we have this th. So I actually imported th. So this is me.shadaj.scalapy.torch. We're using the PyTorch library, which Facebook developed for machine learning, which is a really great library for experimenting with deep neural networks. And I've just renamed it to th, which is a common pattern in Python code as well. So I'm going to start by taking th. I'm going to cast it to dynamic because we don't have the full static types yet. So we want to call a specific method which isn't supported by the static types. We're going to get a device. So here I'm actually training on an RTX 2070 Super, which I got over quarantine. Since we have a GPU available, we'll use that for training. And here you'll notice that this is actually a statically typed API. So th.cuda.isAvailable is actually a statically typed API. So we have some statically typed APIs, some that aren't. All right, next, let's import the transformers library. So transformers is a really excellent Python library for these types of deep neural networks for natural language. So it supports it has pre-built implementations of GPT-2, BERT, and a bunch of other models. And this is from the folks at Hugging Face. So we're going to take our transformers library and we just import it using a single line. We're just going to say py.module transformers, and we have the transformers library imported. Next, we're going to take the GPT-2 tokenizer. So we want to take our strings, but before we pass them into a neural network, we have to tokenize them, convert our strings of words into a bunch of numbers. So we're going to take the tokenizer for the GPT-2 model. And what we're going to do is for every line in our parsed sources, which again is the training data that we generated, we're just going to take the GPT-2 tokenizer and call it and tokenize all the inputs in our all the words in each string. So you'll see this pipestep.run and pipestep.group. This is actually something I'll be open sourcing soon. This is a library that makes it easy to get nice looking progress bars for Scala code where you have a bunch of different tasks that you're running. So this will just give us a nice UI when we're running this to check on the progress of our tokenizer. So here we're just going to say, okay, we're going to map all these parse sources. For each of these, this is a unit of work. And we're going to group these together under the tokenization task. And now we finally get to the model training. So now we have all of our inputs. They're all tokenized, and this is our training data. Now let's say we'll create a GPT-2 model. So we're just going to use the transformers library again. Now here you'll notice everything is dynamic. So this is untyped because we don't have static types for the transformers library yet. But we can just call it as if it was a regular Scala API. So I'm going to be creating a GPT-2 model, which is designed for generating text from a pre-trained model. So we're going to be starting off with like a baseline GPT model, which will allow us to fine-tune it to the Scala code completion task without too much training. We'll be able to do a little bit of training because the GPT-2 model has never seen Scala code before, but it's seen English sentences. It might have seen a few snippets of Python code on Reddit. So it has some kind of basic idea of how to generate text, but we're going to be training it to generate Scala text. Now, we already loaded our device earlier. This is our GPU device. So we're going to move this model onto our GPU for training. After this, we're going to be setting up a optimizer. So there are a bunch of different optimizer algorithms. There's like simple ones like stochastic gradient descent. We're going to be using Atom and a slight variant of it, but this allows us to have adaptive learning rate. So the learning rate will actually adjust based on how the optimization is proceeding, and this works really well for these types of deep neural networks. Lastly, we're going to have a couple of configuration parameters. So we're going to define the batch size to be 16. That just means that we're going to be training on 16 examples simultaneously over and over again. The reason this can't be the full size of all of our input text is because that amount of data would not fit on our GPU. So we're going to be loading 16 examples at a time onto the GPU, performing training, and then continuing after that. All right, and now let's do some live coding to implement our training loop. So this is going to be the core part of our algorithm to actually perform the training. So what we'll do is I'll run a pipe step. So I'm going to be running a pipe step where I'm going to have a sequential. So this is again for progress bars. So I'm going to have a sequential pipe step. Let's just call it. And in the first loop of our training loop, we're going to be looping over epochs. So for each epoch, which is basically in each epoch, you go over all of the training data once. So in this case, we're actually just going to have one epoch, but just so that we have kind of this code is more flexible, we're going to have this epochs variable. So for each epoch, we're going to do some work, and we'll just call this epoch. This is the label for our progress bar. Now within each epoch, we're going to take our batches. So this is something we haven't done yet. So we have our training inputs, but we need to now group them into batches. And this is where Scala comes in. In Python, this would actually be not super trivial, but in Scala, what we can do is we'll have our batches is going to be our training data, which is training inputs tokenized. We're going to shuffle them with scala.random. And I'll have to probably import scala.random. Yes. Scala.util.random. So scala.util.random lets us shuffle a bunch of data. Then I'm just going to group into groups of the batch size. And this gives us an iterator. I'm just going to convert this back into a sequence. So now we have all of our training data randomized, shuffled around, and in groups of our batches. 1, 2 epochs. So now all we have to do is we'll have a pipe step dot grouped because we're going to group these all under a single task. We're going to call this our batch. And all we're going to do is take our batches and map them. And there should also be a map since we need to keep track of our nested tasks. And for each batch, now we can actually run training. There are a couple steps. First, we need to get the inputs loaded onto the device that our neural network will actually use. So first, we'll have our input IDs batch, which is our batch of the input IDs from our tokenizer. So these are the IDs we generated for each token. So the way we're going to do this is we'll take our, we're going to take PyTorch. We'll get the dynamic API out of it. Py.dynamic to get the dynamic API, and we're going to stack a bunch of vectors together. Because again, we have a vector for each element in our batch, and we want to fuse them together into a single tensor that we can load onto the GPU. So we're going to take each of our batches, and we're going to map it. Again, because our batches are regular Scala sequences, we can take each element, and we're going to get the input IDs out of them. So this tokenizer process actually returns, so when we call the tokenizer, it'll return us a dictionary of data in Python. So we can access elements from the dictionary by just doing e.bracket access, which corresponds to using brackets in Python. And we can say, I want the input IDs for each of these elements in our batch. And we're going to take this resulting tensor, which stack gives us. So let me first. So we have a Scala sequence. Again, you'll remember the Scala sequences have to be manually converted to Python because we have two options. I'm going to convert it as a proxy so that we don't have to spend too much memory. So we convert it as a proxy. We send it. We stack them together, and we'll move it to our GPU device. We'll do the same thing for the mask. The reason we need a mask is because inputs are of different lengths, so we have to mask off the inputs to make sure that we don't spend training time on just padded inputs, because all of our input text has to be of the same size, but we might have inputs that are shorter, so we just mask off the padding elements. So we'll have attention, or just mask batch, and all we have to do is get attention mask from each of these. And actually, this should be a pipe step. .unit, and we're going to be using pi.local here. So this is something I didn't explain earlier. Pi.local basically says that all of the Python values that are going to be created within this block will not escape. And this allows us to handle garbage collection much nicer because we can immediately delete all of the values that would have been are allocated within this block, since we're just doing some training here. All right. So now that we have all of our inputs, we can compute the loss. And we can do the loss by just calling our GPT-2 model. So we're going to take our GPT-2, call it, and we have to use this call notation just so we get a dynamically typed API. So we'll pass in the input IDs batch, and then we'll have labels, which is the target. What do we want the network to predict? And that will let us calculate our loss. This is just going to be input IDs, right? Because the goal is for each element in the input to just predict the next word. And we already have that in our input IDs. So we can just set the labels to be the input IDs. Then we have the attention mask. So we'll have attention mask is going to be the mask batch. And token type IDs is pi.none. This is just an extra API that we have to use in this training mode. OK, so this gives us our loss. This is actually going to give us a sequence of PyTorch tensors. So we can just convert this using the as method to take a Python value and convert it into a Scala static type. And this is going to be a th.tensor.tensor. And now we're using some of the static types we generated for PyTorch. All right. So we're going to have to go a little faster now. So we're going to take the loss, which is going to give us a single value. It's actually going to be a sequence with a single value. And that's going to be our tensor representing the actual loss. So now all we have to do is call backward on this, which says perform back propagation to actually compute the gradient of how we need to adjust the weights in our model to improve our loss. Before we do this, actually, one thing I forgot to do is we need to actually zero out the gradients. So we're going to do GPT-2.zero grad. So this will zero out the gradients just from our previous iteration. We call backward. And lastly, and once we've computed the gradient, we can perform our optimization step. So we can take a step off our optimizer now that we have our gradients. And lastly, I'm just going to return some reporting information. So I'm going to say that we're going to return nothing, and we're going to say that we're going to do we're performing training, and our loss is %d %.2f, something like that. We'll have to make sure that this code is correct. I'll just check against my backup. And the way we're going to get the loss is take the tensor and get its item and convert it to a Scala double. This will give us our loss. So assuming I've done everything correct, I'm just going to start running this because this takes about 3 minutes to run and we're getting low on time. So I'm just going to start running this and hopefully it will work. And all my live coding worked fine. So it's going to run. In the meantime, I'll jump back to my slides and we'll check in a bit if this works or whether I made a mistake in my live coding. So in our remaining 3-ish minutes, let's quickly cover static types in ScalaPy. So ScalaPy lets you maintain type safety while you're dealing with Python APIs. So first, you have a bunch of mappings between core Scala types and core Python types, and this is automatically handled by ScalaPy. But ScalaPy also comes with a full type hierarchy representing Python values. So for example, you can have statically typed APIs for Python objects and different types of objects and different types of modules. And this gives you basically an equivalent of the Python type hierarchy within your Scala code. ScalaPy makes it easy to create facades, and this will remind you of the way you create facades in Scala.js. So for example, if I want to interface with the random module in a statically typed manner, and this is a module from Python, I can just define the kind of API interface I want, have the implementation be py.native to say, go to Python to actually execute this method. But now from Scala, I have a nice statically typed interface for all of this. You can use this for some advanced type checking. So this is a project from Maxime at EPFL, who is a master's student, who worked on actually having a shape-safe interface to TensorFlow. So this means that it'll check all of the dimensions of all of your tensors to make sure that they line up. So you can use these type facades for some really powerful type checking. And what I'm really excited about today is that with ScalaPy 0.5, we have a really early pre-alpha version of generating static types. So based on open source type definitions available through MyPy, which is a Python type checker, we can actually generate Scala types. So in the remaining 2 minutes, and we're lucky here because this demo is a bit shorter, we're going to be looking at another application of ScalaPy for mixed integer programming. So briefly, mixed integer programming basically lets you do linear programming, where you have a bunch of linear constraints and a linear optimization target. But instead of trying to figure out whatever floating point value of your variables optimizes that, you instead have to pick integer values for those. And that makes this an NP-hard problem, but Python has solvers for this that we can use. So let's code. OK, it seems to have crashed in the meantime. Class stack argument tensors must be a tuple of tensors. OK, I think we should have created a copy, which will create a list instead. OK, yeah, that's right. OK, so let's quickly swap this out with to Python copy. And in whatever time I have left, let me kill my SBT and start training. So maybe during the Q&A, we'll have the results of this. OK, so let's start running. And in the meantime, let's look at this mixed integer programming solution. So let's start training in the I mistyped. Let's start training in the background. Oh, I need my Python environment to load up. Okay. Ooh, the dangers of live coding are fun. All right, so we're going to start training in the background. So we're going to be solving the knapsack problem, where you want to pick items from a bunch of choices to maximize the profit while keeping the weight under some limit. So we're going to be using the Python MIP library for this. So let's really quickly create a model. So I'm going to create my model is mip.model.model. And we're going to have this be a maximization problem because we want to maximize the profit. So what we're going to be doing is we're going to be creating a binary variable for each item, which represents whether we include it in our knapsack or not. So we're going to basically have item variables, which is we're going to take each item in our items and map it. So we're going to take our item and we're going to pair it with a Boolean variable. So we're going to take our item, but we're also going to add a variable to our model. And again, you're seeing that I'm getting code completion because this is all statically typed. We're going to create a variable. The var type is going to be binary, and that's it. So we have a binary variable for each of our items. The first thing we need to add is a constraint. So we're going to say that the items cannot exceed the weight of our knapsack. So we're going to add a constraint. What we're going to do is we're going to say mip.model.xsum, which is a way to say I want to sum up all these values. I'm going to take all of my item variables, and for each variable, the weight each item contributes to the knapsack is going to be whether it's included, which is t._2 times the weight of the item, which is t._1.weight. And I'll convert this to a Python copy. So what we're saying is that the sum of all of these variables, and again, this is all statically typed, less than or equal to is also statically typed here, has to be less than the max weight. This is all statically typed to make sure this is actually a linear expression. And lastly, we're just going to set the target. So we're going to say we want to set the objective. So we want what we want to maximize is going to be a very similar expression, but instead of we don't want to maximize the weight. We want to maximize the value of the items we took. So now all we have to do is model.optimize, and we see that the training is working in the background. So I did do my live coding right after that fix, but we're going to optimize our MIP model. And once we optimize it, all we have to do is take each of our items and see what the model picked. So once this optimization is done, for each item, we're going to have our item and the variable that we use to represent whether that item is included or not. We're going to extract out the variable's value. So we're going to get the 0th value since each variable only has a single value in our case. We're going to convert this to a double because these are represented internally in the library as doubles. And we'll just round it. And if this is 1, which means that we took it, then we'll print our item. And that's it. So let me actually boot up SPT in another tab just so that we can quickly show you the results of this since we are a little bit over time. So let's run, and let's run our MIP demo. So it's going to generate the model. Oh, no, I need my environment. I use NixOS, so you have to run your shell for another line for it to load up your environment. OK, so we're going to run our model. Oh, no, no module named MIP. Oh, OK, let me install MIP. I think I forgot to install it when setting up my environment for the demo. OK, so again, you'll notice here I just used pip, which is the Python package manager. Anything that you do in Python works with ScalaPy out of the box. So let me run our model, and we get the best objective found. So we're using the Gurobi optimizer, which is a really powerful optimizer for these linear mixed integer programming problems. And we see that we found the best objective, and these are the 3 knapsack items that we want to include if we want to stay below the max weight, but get the highest profit. And this is entirely statically typed. All of the API calls, you get code completion for everything. And this is all generated by our alpha static type generator. So no manual types had to be written for this application. And so with ScalaPy, you can do lots of really cool applications without writing any code. And just in time, we have 2 seconds left and our model training is done. We've saved our model. And for the fantastic demo at the end, we're going to run inference. So we saved the model, and now we can run inference with our trained model. All the inference script, which I've already written here, again, using ScalaPy, it's just going to load our model and then let us code complete different things. So for example, I could say, let's say I have val auth. What could you code complete with this? Well, we can see val auth is request header, author maybe, auth email message, auth equals OAuth, auth is new auth. So you'll see that these are not necessarily the best examples of code completed Scala code. And that's because we trained it in maybe 5 minutes. If you spend a lot more time, you'll get much better results. But for a model that's never seen Scala code before, we're getting some fairly reasonable results. If I, for example, say case class, let's see what we produce. We get case class perf. We get some chess-related things because we trained on a chess database. Case class extends any val, so we get some implicits. And this is all being generated by a deep neural network model that we just trained in 5 minutes using ScalaPy on Scala code. So we're a bit over time, but that's it. So if you want to try out ScalaPy, version 0.5 is out today. ScalaPy lets you use Python libraries from Scala code in JVM and native code with a seamless interoperability layer that lets you use all these types of libraries, from deep learning to mixed integer programming to anything you can imagine with a fully type-safe layer. So you can get started today at scalapy.dev. And thanks for coming. Cool. All right, I don't know if we have questions now or.
Hey, thank you so much for your talk, Shadaj. We do have a couple of questions that I'd like to ask you live. Let's dive in.
All right.
First question is, can you make a Python proxy on a mutable sequence? And if you do so, are changes on one side forwarded to the other correctly?
They are. So that's one of the features. So one of the cool things actually is, let me open up, maybe I'll just try opening up a console. So I can import me.church.scalapy.py, and let me also import the seq converters, py.seq conversions, I think, seq converters. There we go. Okay, so if I do this, I can create a mutable sequence. So if I, for example, create val my seq is a mutable dot scala.collection dot mutable dot seq 1, 2, 3. Let me convert to a Python value. Python value is going to be my seq.to Python proxy. I can, oh no, what happened? Oh, I didn't have my environment set up again. Okay, whatever. You can take a look at the ScalaPy websites. It's actually there in the docs. But yes, if you take a mutable Scala sequence, convert it with a proxy, Python will observe all changes to that. And in fact, if you choose to expose a mutable sequence in a future version of ScalaPy, Python will be able to mutate it back. So with proxies, you have two-way conversions, and you can observe changes on both ends.
Thanks. We have a couple more questions. The next is, are other Python types such as dicts supported? Those correspond to a Scala map.
Yes, dictionaries are supported, not to the full extent as sequences. We haven't fully optimized them yet. You can convert maps into Python dictionaries and Python dictionaries into Scala maps. You can do that just using dot as and your map type if you want to convert a Python dictionary into a Scala map. We don't have full bidirectionality of mutable maps yet. That's something that will come probably in the next release.
Great, thank you. Next question, when can we expect an alpha IDE with this implemented?
So my guess is the IDE is referring to code completion or things like that. So right now I'm using metals, and the types that you generate are actually just regular Scala sources. So if I go to facades, you can see that I have all my types that I generated, which are just these like huge Scala sources with a bunch of type definitions. The result of that is that if you're using a IDE or language server like metals, everything just works out of the box. One of the cool things that I would love to see in the future, but it's going to be a lot of work. But if anyone in the open source community wants to contribute, is code completion for dynamic types. It is possible in theory, especially in Jupyter notebooks, because you could introspect your runtime Python values, but I think that will take a lot more time to make it into ScalaPy.
Gotcha. Our last question is, does ScalaPy already support Scala 3?
So yes and no. So as a result of Scala 2.13 being compatible with Scala 3, you can use it in Scala 3, and most of the features will work, except for type facades, which do rely on macros. However, I'm really excited that this summer, we have a Google Summer of Code student who's actually going to be working on bringing full support for Scala 3 to ScalaPy. So stay tuned for that.
Sounds great. Well, thank you so much for your talk. Thank you for joining us. We hope you enjoyed the conference and have a great rest of your day.
Great. Bye.